dynamics of dissipation and power input. Have you ever watched a machine running and wondered, how the invisible forces driving it actually work behind the scenes? Well, you are in the exact right place. Today we're tackling the fundamental mystery of system efficiency and energy movement. And honestly, by the time we wrap up this explainer, you're going to look at the physical world in a completely different, highly structured way.
So consider this central question. Where does the missing energy actually go? We see it all the time, right? Literally, no process is perfectly efficient. Your car engine gets burning hot, your laptop fan spins up like crazy when it's working hard, a bouncing ball, well, it eventually just stops bouncing. We usually say that energy was lost, but framing it as lost energy, that's actually totally the wrong way to think about it. Instead, we need to treat this drop in efficiency not as a disappearance, but as a real, thrilling scientific mystery waiting to be solved. Because the energy didn't just vanish into thin air, it just went into hiding.
Section 1. The Leaky Pipe Mystery. Okay, let's dive into this. To figure out where that energy went, we kind of have to treat the system like a crime scene. A great way to look at this is through a brilliant narrative analogy from our source material called the case of the leaky pipe. Imagine a massive, fully functional pipe, meant to carry rushing water from point A to point B. Now, if that pipe gets a crack in it, water is going to spray out the sides long before it ever reaches its final destination. The system is still technically working, right? But the overall efficiency is dropping fast because of that leak. In our physical systems, energy flux operates the exact same way. Energy is literally leaking out of our functional system, and we need to find the crack.
There are 3 fundamental principles to guide our little investigation here. First up, energy movement is constantly happening within any functioning system. Second, because of all that movement, system efficiency inevitably drops over time. That's just a fact of life. But the third point, that's the golden rule of our investigation. Energy is never truly lost. The universe is like an incredibly strict accountant. You absolutely cannot destroy energy. Which means, if the efficiency drops in any process we run, the energy didn't just cease to exist, we just need to track down exactly where it leaked out of the pipe.
Section 2. Meet the power sources.
Before we catch our culprit, we need to meet the benefactors, the things actually driving power into our system. I mean, you can't have a leak if you don't have water flowing into the pipe to begin with, right? The first power source is called the effort source, represented by the symbol SE. Effort sources provide a baseline power input to a system. The absolute perfect example of this is just the physical force of gravity. Think about a boulder rolling down a huge hill, or water flowing down a mountain stream. Gravity is this constant, steady effort providing power to that system. It's a natural, inherent driver pushing energy right into our setup.
Next up, we have flow sources, which are denoted as SF. If effort sources are like the natural, passive pull of gravity, flow sources are the mechanisms actively driving and forcing energy into a system. Think of motors as the prime example here. A motor isn't just some passive physical force, it's an active, mechanical device that is purposefully built to push functional energy or flow into our system.
And this brilliantly illustrates the whole dynamic at play. On one hand, you have effort sources like gravity, acting as this subtle, omnipresent force. And on the other hand, you have flow sources like motors, which actively and forcefully inject energy into a process. Together, these 2 types of sources represent the fundamental ways we supply raw power into any system we want to analyze. They are the water entering our metaphorical pipe.
Section 3. Catching the energy thief.
So we know exactly how the energy enters, but the pipe is still leaking. It's time to reveal the culprit. The thieves in our system are the resistors, symbolized by the letter R. Resistors act as, well, the energy thief. But remember our golden rule? Energy is never truly lost or destroyed. So these resistors don't eliminate the energy, instead they essentially launder it. They take functional, useful energy that was meant to do real work and they convert it into exhaust heat. They are the exact hole in our leaky pipe, just spraying our valuable energy out into the surrounding environment as useless warmth. To make this abstract concept of a resistor a bit more of a physical reality, look directly at friction. Friction equals exhaust heat. Try this. If you rub your hands together really fast right now, what happens? You are acting as a flow source, using your muscles to input mechanical energy. But your hands heat up, right? That friction is acting as a resistor. It's literally stealing a portion of your mechanical energy and laundering it away into exhaust heat. It is a perfect, everyday visualization of exactly how energy gets stolen from a useful process.
Section 4. Mapping the energy flux. Let's move to and see how this builds into the actual tools we use to track this energy balance.
Now, what's really interesting about this slide is how clearly it proves the math of our universe. Your total initial power supply, so everything from gravity and motors combined, will always perfectly equal the functional useful energy plus the dissipation, which is our exhaust heat. The energy didn't disappear into a black hole. No way. It just split into two completely different pathways. We get the useful work we wanted alongside the heat that we didn't.
This beautifully synthesizes everything we've uncovered. When you map your power inputs directly against the dissipation mechanisms, you can really visualize the balance. Doing this allows you to look at any physical scenario and instantly identify what is pushing the energy in and what is actively stealing it away. So, the crucial point is this simple 3-step procedure. This is your main learning goal from our source material today. Step 1, map your system inputs. Find your SE and SF. Step 2, track the energy flux. Actually follow where the power is trying to go. And step 3, identify exactly where that energy exits the system as exhaust heat via your resistors. If you can follow these 3 steps, you can solve the leaky pipe mystery in absolutely any process you ever encounter.
I want to leave you with this final, somewhat provocative thought. Next time you are looking at a machine, a moving vehicle, or honestly, even your own computer, remember that energy never truly disappears. Look past what the machine is supposed to be doing and ask yourself, what is your system really powering? Are you running a highly efficient machine, or are you actually just powering a really elaborate, unintended space heater? The answer is always found in the balance of input and exhaust. Keep that in mind, and you will never look at the physical world the same way again. Thanks for joining me on this explainer.